Hi geometry students, welcome to the lesson for 10.1. Welcome to chapter 10. We have a lot of new vocabulary in this lesson, but I don't think it's particularly hard vocabulary. It's just a lot of stuff that we have to know the definition of or know what it is in the context of some pictures. We're going to mostly draw pictures rather than, I think, boringly, formally defining these. We're going to look at the pictures instead and say, this is what a circle is, this is what the center is, this is what the radius is, and so on. You should know the formal definitions, but we are not going to take the time to write all that down. And some extra examples in your book to help you as you go along here. Let's start off by drawing a circle. If you have some coins, maybe some quarters, nickels, dimes, pennies, something like that, you might want to get those out right now. You might want to use those for this chapter. I think you could find that very helpful in drawing nice circles. We're going to definitely want to draw some nice circles as we go with this chapter. So pause the video if you would like to do that. If you got some coins, go get those, and that'll make your drawings look a lot nicer. It will make your notes a lot more helpful. I'm not requiring perfection on these notes, but the better you can make your drawings, the more helpful it's going to be. So let's start off with a circle. If you had a compass, you could use that too, but draw a decent sized circle. Make like a quarter size, maybe even a $50 size, the JFK coin there. Have one of those, or you could use a small bottle or can or something like that. You could use that to help you draw some nicer circles. So draw something like that. Also get a straight edge, something straight to draw a straight line with, I guess, for lack of a better term. Nothing else is coming to me. So some straight lines. I want you to draw. This one is just going to touch the circle like that, and we'll put some arrows on that. So it's a line. It continues forever in both directions. This one's going to cross through the circle at two different points, but not through the center of the circle. So make some arrows like that. If you had your ID, you could use the edge of an ID. If you have a ruler, you can use that. Find the center of the circle as best you can. Right here would be about the center, and then I want you to put a point there, and then also get out the straight line tool again. I'll get my straight line tool out again. I'm going to say from here, that point where they intersect, going over through the center of the circle to another point on the circle. That's going to be another one, and I'm going to have one more right there from that center point to a point on the circle right there. Okay, let's define some things based on what we have here in this picture. Let's label this line K though first, and this one line L. Use a cursive L for that so it doesn't look like a 1. And I'm going to go with the letters O, R, N, and I. I think I was going for iron here. I-R-O-N. The center point of this picture, well, the center is just where it's centered at. The center point in this picture is point R. It's always a single point. Point R is a center point. What would a radius be? Radius of this, or radius, we should know this from previous math classes, from this book as well, from geometry. We've talked about radii before. That would be plural for a radius, not radiuses. We say radii instead. So this would be, one possibility would be from I to R. It's from a center point to a point on the circle. A circle is just a set of all points the same distance away from that center point, and equidistant, in other words. And then a radius is going to be from the center point to any particular point on the circle. So one radius would be segment IR. If you just said the distance from I to R, that's more of a number value, but the segment itself is a radius technically. Rn would be another. Could you call it NR? Could you call this Ri? Sure. Either one of those would work. And also there's one more, OR. You could also say RO. The diameter for this circle is going all the way across. It's twice as big as the radius. It's like two radii connected together, but in a perfectly straight line. So I to O, you could also say O to I. Either direction works just fine. So radius twice as big as the diameter. Let's put a little note of that in a different color. So take out a different color at this point. radius, and you'll say this, and you go times 2. That's the same thing as the diameter in terms of a distance. So you have to have a perfectly straight line, though. I-O would be a radius. I to N is not a radius because it's not going through the center of the circle. So it has to connect two radii in a perfectly straight line. Chord, this is probably a new term for a lot of you. A chord is something like what you have here, I to N. It's just any segment connecting 2 points on the circle. So IN works. What also works? IO also works. So let's write this down. I feel like this is important enough where it's a newer one, a newer term for a lot of us. Let's write a short definition down. A chord is any segment connecting, not connected, but connecting 2 points on a circle. That's why IO also works. Yes, it's a diameter, but it's also a chord because it connects a point here to a point here. So that's what a chord is. A secant would be a line that goes through 2 points on the circle. So it's a line L in this case. Or you could say an equivalent thing to say would be, let's underline these two. So radius, diameter, center, chord was that. Secant right here, line L. You could also say that it's the same thing as line IN. Remember, with our line symbols, we put the little line there with the two arrows like that. A secant is any line that goes through 2 points on a circle. So very close in relationship to a chord. It's like a chord, but with arrows going forever in both directions. And a tangent, this is not sine cosine tangent now, it's a different definition of tangent, would be line K. This is any line that just touches 1 point. So right here, I'm saying that's the particular point right here. Right there's the point of tangency. We're going to learn about that in the next one, the next slide, a little bit more. So this is a connects, just touches, there we go, touches 1 point on a circle. Okay, so that's a lot of our vocab from back here. That covers up to here, it looks like, actually. So we've hit all that stuff. We should know what all those words mean based on that picture right there. And let's draw some more things here. You can take out your coins, or you can do this freehand as best as you can, but the better your pictures are, again, the more helpful it's going to be later. So let's draw some circles. Don't draw it yet. I'm going to move things around. So don't draw it like you see it quite yet until I say you can do that. So there's a good one. Draw a picture that looks like that, and then also draw very close in proximity to that. Draw a picture kind of like that one there, and that's, yeah, that's just wanting to touch right there. Okay, that's good to go right now. These are called tangent circles. When we saw tangent lines, they just touched the circle at 1 point. Tangent circles just touch each other at 1 point. So that just touches right there. That's just touching right there. If you zoomed in really, really close to these points here and here, you would see they're touching at just 1 point. So tangent circles, these are examples of tangent circles right here. These would be examples of, so don't draw it yet. Wait for it, wait for it. Right about like that. Yeah, that will work. They have the same center point. We're going to say that center point's right about there. These would be examples. Let's group this together. Circle that. That's tangent circles. These are called concentric circles. Kind of with the same center. Concentric with the same center. So concentric circles, there we go, have the same center. You could have 3 of them, you could have 4 of them, they all just have to have the same center. Another picture I'd like you to draw looks like this. So draw a circle and draw a line, a tangent line here. Draw a tangent line. We know it's a line because it goes forever in both directions, and we know it's a tangent line because it just touches right there. Then I want you to label some points in here. So point A is just somewhere in there. It's not the center necessarily, but it's somewhere inside the circle. Point P is the point right there where the line and circle meet, and point E is just some point hanging out outside the circle somewhere. So point P, this is the point, we mentioned this earlier, the point of tangency. It's that tangent point right here, point of tangency. A would be in the interior of the circle, interior. And E would be outside of the circle, exterior. Or you could say an exterior point and an interior point. So that all goes together with that picture. Let's circle that. And then we're going to have one more picture where I want you to draw two circles. Sorry, not a line, but two circles. There we go. Let's make one of them a bit bigger than the other one. We'll do something like that. Okay, so two circles. I'm going to call this one, we label circles according to their center point. So this would be called circle A if I labeled that with an A. This would be called circle B if I labeled it with a B. And there's A, there's B. I want us to draw in some different lines here. So get a straight implement of some sort and draw some different lines in here. Don't draw these quite yet until I give you the good to go with each one, because I'm going to need to adjust these a little bit to make sure that they're just touching. So actually let me just do something like this. I think that'll probably be my best way to go. Okay, so I'm trying to draw these so that they're just touching. So there's a good one. Draw a line kind of like that, and then do the same sort of thing towards the bottom. See if I can get this. It's close. Okay, I'm just going to move that just a little bit up. So draw another one where they're just touching. Let's put some arrows on those. And then I want you to draw some other lines in here as well where they kind of cross like this. Ooh, that was nice. Got it. First try. And then another one, same sort of thing, going in this direction. Close on that one, no cigar though. Why is that a phrase? I'm just thinking about that. Close but no cigar. Why is that a common phrase? I don't know. Where do a lot of the catchphrases we have come from? I don't know. Okay, so we've got 4 different lines here. Got a lot going on in this picture. Let's call this one line J. Let's call this one line N. This one M, using lowercase letters for all my lines here. And line K right there. And then I want to draw, let's draw this in red, or whatever color you have. We're going to draw connect points A and B. So use a color for that. Connect those points. I'm going to mention some stuff about that segment and what makes these what. So we've got J and K. These are tangent lines, yes, but let's be a little more specific. What kind of tangent lines are they? They are tangent lines. They have the circles in common. They're common tangents, in other words, and they are internal because they're crossing kind of in between the two circles, not along the outside like N and M are. So they're crossing in between. Another way to look at it is that they cross the segment connecting the two center points of the circles. So J and K are called our common internal tangents. And M and N are common external tangents. So they're tangent lines. They're tangent to both circles. They have both circles in common, in other words. One kind of goes on the outside or the exterior of both circles, and the other ones, M and N on the outside, J and K, kind of cross along the inside in a sense. And so in a different color, let's color code this. I think that's going to be pretty helpful here. This was where they intersect. Segment AB, the segment connecting their center points, their respective center points of the circles. These was where they don't intersect that segment. So where they don't intersect segment AB. So that goes with that part. That goes with that part. Different color with that stuff, please. And let's put all this together. So just to make sure that you know what goes with what, let's circle all that stuff there. So J and K common internal tangents, and let's underline what we've defined here. We've defined this in terms of, or in the context of a picture, common internal and external tangents. We've defined point of tangency, we've defined interior, we've defined exterior, we've defined tangent circles, and we've defined concentric circles. So I think that might be the rest of the definitions. Let's take a look back here, and that will do it. Yep, we got everything. So we got all the vocabulary down. You got to know the basics. These are the basic terms of circles. So go back and pause, rewind, review as needed with that, and from there we will move on to some examples. Before I move on with those examples, though, I want to insert, it's talking about the book a little bit. So I've got the book on a nice PDF format here. I'm looking down at the theorems. There we go. So if you feel like writing these down will be helpful for you after we talk about them briefly here, go ahead and do that. That is not required, though. I think they're pretty straightforward. I think they're pretty intuitive, these couple. So if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency, meaning that if it's tangent here, then you could put in a little box in the corner right there and say that that is 90 degrees, that they are perpendicular to one another. And if you start off with them being perpendicular to one another like this, that means the line is tangent. So this is just the converse of that one. This is just that one flipped around. Theorem 10.3, again, write that down if you feel like that's going to help you, if you need to. But just remember, tangent means perpendicular, perpendicular means tangent. That's good enough for you, then you wouldn't have to. And Theorem 10.3 is another one you should know, but I don't feel like it's all that hard to remember or to intuitively think about. So if two segments from the same exterior point are tangent to a circle, here's that exterior point, S. They're tangent here at R and T. They just touch right there. That would mean they are congruent. So ST from here to here, S to T, would be congruent, same measurement, same distance as you would have from S to R. So you could put a little tick mark here. You could put a little tick mark here saying TS is the same as RS, or SR is the same as ST in another way to think of that. Okay, let's check out now this example. So write those theorems down if you feel like you need to, but if you understood those and you're like, oh, that's easy, that's up to you. Let's draw, for example, one. Let's write this down first. Is MU, line MU, tangent to, and we've got a symbol here. We're going to learn a new symbol. This is the symbol for a circle. You draw a mini circle with a center point drawn in there. Is it tangent to circle D? And let's make a note of that right here in a different color, that this is the symbol for the word circle. Okay, that's what that is referring to. Symbol for circle, that's right there. Okay, let's draw in excuse me. It's a normal colored circle. Not too big, not too small. I'll go about like that. Maybe like $half size. Even a small can, maybe like a soda can, that would be getting to the brink of being too big for what we need here. But let's draw in the center points. This is circle D, so this would have to be point D. The center point is how we describe the circle. And let's also draw in some other lines here. So we're going to draw a line there to there. I'm going to make it look tangent, but we need to determine if it actually is. Okay, so we've got something like that. Let's label a few other things here. This is going to be point M. This where the circle and this line meet. It might actually meet at another point. It's just hard to tell right now. This is going to be U. So this is going to be triangle mud, it looks like, and this is 13, I was saying, from D all the way to U. So 13 from D to U. This is going to be 5 as well. So how can we determine if this works? We're going to go back to something we learned a couple chapters ago and use the converse of the Pythagorean theorem. Is this a right triangle? If it was a right triangle, I could put the little mark right there, and then I could go back and think about the theorem right here. So this is the theorem. Which one is it? It would be, if this is true, if they are perpendicular, we'd be using this theorem. If you had that, you could draw that in, then you would say they're tangent. If we can't say that they are perpendicular there, then we can't say that they're tangent. Let's see though. Let's see if it works out. So the converse of the Pythagorean theorem, do you remember doing something like this? Leg squared, potential leg squared plus potential leg squared, two smallest sides squared. What is that compared to c squared? So I think before when we did it, let's actually do this. We compared c squared to a squared plus b squared. We put it in that order. You can compare it in the order I just had it to, but let's keep it consistent with the way I had it before. So 13 squared is what, question mark, what compared to 5 squared plus 12 squared? What is that comparison? 13 squared, that's 169. And we still are going to put a question mark here, not totally sure yet. 5 squared is 25, and 12 squared is 144. So if we compare those two, you got 169 equals 169. Therefore, since c squared equals a squared plus b squared, let's write down what that was again. That was the converse of the Pythagorean theorem. That means by theorem 1012, or 10.2, sorry, not 1012, 10.2, line MU, is it tangent? That was the question, is it tangent? It is tangent, yes. MU is tangent to circle D. And that's the answer part of our question, but we need to reason that through. So showing the work for something like that. So what could we actually do in the picture? If we wanted to, we could then add the right angle in the picture. We know that it's not acute, we know that it's not obtuse, we know that it's a right angle because they are equal to each other. Okay. And let's do one more example here. That may look familiar to some of you. That is the Quartz Hill Water Tower. We're going to use what we're learning about here to find the measurements of the radius of a water tower without actually taking a direct measurement of it. This is pretty cool, I think. So we can do this with any circular, large circular shape that you might not be able to climb to the top to, or to measure from the center point to the edge there. You can actually figure out how big this is without climbing on top of it. You can use some of the ideas we're learning about here to figure this out. So suppose, let's just put this in parentheses next to this one. This is a circular water tower. Maybe a better way to say that would be cylindrical, but pretend we're just looking at it from straight above, and we're looking at this, it makes a circle if we look at it from straight above. We're going to try to figure out what the radius of this is. So how could we figure out the radius if we couldn't get on top here and actually measure it? you could, well, one thing we could do, I suppose, would be to take lines straight out, but how would you know they're actually tangent? This is, I think, the better way, and even the quicker way if you do it right and know what you're doing. So surveyors, they could use some ideas like this. Let's draw on the center point of our circle there. Not going to give it a label on this one. And then I want you to draw in a triangle, a right triangle. Woo, that is not what I wanted there. Okay, there we go. And I did not want that to break the line. Let's try that one more time. There we are. Okay, and drawing a right triangle like that. We're going to assume this is a right triangle now. We're going to assume that you were walking off a distance and you walked tangent to the circle. So you started at a particular point along the circle and you went that way, and then you stopped right here, and then you turned and looked directly at the center of the circle. You looked right at the center of the water tower. You knew where that was. So this is, let's put that in, that is a right angle. We can be assured of that. This we're going to say is 28 feet. We're going to say you started here and you walked off a distance of 28 feet, and then you walked towards the water tower this way, and you found that from here to the point where you actually came to the water tower, that was 14 feet. How could we possibly figure out the radius of this water tower? Well, we can use the Pythagorean Theorem, it seems, because it's a right triangle. It seems like that would work. Wouldn't this be r from here to here? If this is r as well, that would be the radius as well. So I could put in r right there as well. Let's now think about how we can set this up. So we've got leg squared. We could use 28 for one of the legs. We could use r for the other leg. You're going to have 28 squared plus r squared equals, what's the other part? The hypotenuse. Looks like it's r plus 14. It's from here to here is r plus 14. So look at that. That works out just fine. So let's write this above that. Leg squared plus leg squared equals hypotenuse squared. These were the two legs. This was the hypotenuse. So from here, what do we get? We've got 784 plus r squared. That's going to equal, this is the same thing as saying r plus 14 times itself, r plus 14. There's a shortcut you may have learned about in algebra for the squaring, or for squaring binomials like this. But if you don't remember that shortcut, I bet you do remember FOIL. I bet you remember what that stood for. I hope you do, at least. Let's FOIL this out at this point. So from here, I'm going to rewrite, leave a line right here, leave a space in that line. Let's write F, O, I, and L, and then skip to the next line here. I'm just carrying down what I had up here before. A little algebra review. We haven't used FOIL, multiplying binomials, too much in geometry, but here's a time where it actually comes in handy here. So r plus 14 times r plus 14. You could have written that as 14 plus r times 14 plus r. That's another way we could have thought about it. But first, you're going to multiply r times r. Those are the first two terms. Algebra review time, that's r squared. Outside, or outer, is r times the positive 14. That's going to be a plus 14r. Inner, or inside, that's the inside terms of the binomials, the 14 and the r, another plus 14r, and then last, you have the last two terms. 14 times 14 is 196. Now we can combine like terms together. So this was my FOIL part. Yeah, why don't we put one more circle around here. This was FOILed from up here. And let's now figure out what do we have here. Let's combine like terms first. So r squared, you've got 28 r's right there, 28r. That's the shortcut some of you might remember. It's the first term squared, the last term squared goes here, and then it's 2 times the middle terms squared. You can think of it like that as well. All right, so from here, what we can do is subtract r squared from both sides. What happens when we do that? Something really nice happens. It cancels out both spots. Then we just have an r to deal with. That's easy to solve for. With some basic algebra techniques, we can subtract 196 from both sides. Carry down what we have left. This minus this is 5/88. This would equal, this cancels right here. You'd have 28r. If you divide by 28, you've got your answer. The radius of that was 21 feet. Don't forget your units with a problem like this. So 21 feet is your radius. And then one more note I want you to write down. I'm just going to put this off to the side here. You may find you need help with, if I assign any of these problems for help with W slashes, meaning with, for help with 6 through 8, or 46 through 48, if I assign any of those problems, I want you to look at this example. I'm trying to keep the notes here that you have to take to I can't think of the word. I'm so close, but to an amount that's not too cumbersome. That's a good way to put it. A length that's not too cumbersome for you. So to do that, sometimes I need to point you to the examples in the book. That's what I'm going to do right here. So for help with 6 through 8 or 46 through 48 on the classwork, I want you to see number 7, example 7 on page 598. Beyond that, I think what we talked about here should really give you a good understanding of what is to come and what you're going to be doing on the classwork here. And we'll give you a good foundation for the rest of this chapter too. So we have to know these basic terms of circles to be successful for the rest of this chapter. If you have any questions, let me know in class. Beyond that, have a good day, and I will catch you guys later.